The space race spurred fierce competition to be the first to receive a signal from another world. Within a few years, Soviet astronomers declared victory. Discovery of a steady signal that indicated a distant alien civilization. Strangely rhythmic radio transmissions, such as never heard before, were coming from a celestial body they designated CTA-102. Everyone's excitement proved premature. What the Russians actually had found was in fact coming from what's called a quasar. They weren't hearing a big hello from the heavens, but natural radio pulses from the nucleus of a young, faraway galaxy. Undaunted, the search for extraterrestrial intelligence plunged ahead. In 1967, British astronomers announced a precisely timed radio signal coming from 4 separate places in the sky. They dubbed them LGM 1 through 4. LGM stood for Little Green Men. Another false alarm. In truth, they had discovered pulsars, dying stars that naturally emit radio pulses. No little green men, but the search was adding constantly to our knowledge of the universe. Since Frank Drake's first experiments in the early 60s, SETI has become accepted by the scientific community as a legitimate and important part of the research landscape. More than 60 projects around the world have concentrated on picking up that first otherworldly signal.
It's one of the few modern science experiments that just about everybody can understand. SETI is a fairly sophisticated endeavor. This is a hard thing to do, but everybody understands what it's about. It's very simple what it's about. We're simply trying to find out if there's anything intelligent out there. So it's an accessible kind of science.
I think I've got the best job in the entire world. I mean, I learn something new every day on a huge range of different topics because there's almost nothing that doesn't bear on this question about the probability of life somewhere else in the universe. I certainly have a lot of colleagues who would not choose to do this job because there's no guaranteed payoff.
For a short time in the early 1990s, SETI received money from NASA, but a budget-slashing Congress voted to kill funding after only a year. Since then, Jill Tarter and most of the SETI scientists have relied on private donations.
EWA 517, do you want to report a UFO? Over. EWA 517, do you want to report a UFO? Over. Negative.
Attention from Hollywood and the public's obsession with UFOs have helped in a lot of ways, but hurt in others.
Many people think that what we do is of the same ilk, if you will, as the pseudoscience claims and the UFO claims, and they don't distinguish us. And that reduces our credibility and reduces our ability to get support and to get the respect we deserve.
Although much of the public's interest has been fueled by our appetite for science fiction, the search for ET intelligence is real science. Recent discoveries in other areas of astronomy, as well as biology and physics, make the possibility of alien life more likely than ever before. If ET is out there, the odds are better than ever that we'll find him. In the vastness of outer space, we of Earth are reaching out, seeking confirmation that there are other worlds where civilizations live and thrive. It's a search that began small, just 4 decades ago. Carl Sagan was one of the earliest and staunchest believers in the quest for ET intelligence. In 1961, Sagan was one of a group of scientists assembled by Dr. Frank Drake to develop a game plan to search for signs of intelligent life in the cosmos. To guide the discussion, Drake ingeniously devised a formula. 4 decades later, it's still known as the Drake equation, a sort of recipe for the probability of intelligent alien life. Those at SETI believe the Drake equation may one day be considered as important as Einstein's E = mc squared.
The Drake equation is basically a fabulous way to organize our ignorance. It has no known answer. So it isn't an equation that you can calculate a believable answer. But it does really help us think about the probability of life being somewhere else.
It may be a little scary looking, but it's actually rather simple.
The Drake equation gives us a number, the number of detectable civilizations in space, which we like to write with a large N. We arrive at that number by making use of the information we have about the evolution of our galaxy.
The rest of the equation consists of a series of simple questions.
The first term in the equation, which is R, essentially gives the total number of possible sites for life in the galaxy, the total number of stars. Now, we know that fairly accurately. It's on the order of maybe 400 billion stars. We know that by looking at other galaxies and just adding up the total amount of light coming from those things, and that tells you how many stars there are. It's really quite simple.
With newer and better instruments, such as the Hubble Space Telescope, we're gazing beyond our solar system more clearly than ever before, seeing more and more star systems that are candidates for alien life. We now know that there are more stars in the universe than there are grains of sand on every single beach of our planet. And more are born each and every year. In the search for extraterrestrial intelligence, it seems there will never be a shortage of star systems to explore. The second term in the Drake equation, FP, is the fraction of stars that have planets. Until recently, there was no proof of planets outside the 9 of our own solar system. But in 1995, 2 Swiss astronomers detected a strange wobble in a star. A wobble they determined was caused by the gravitational pull of an enormous planet orbiting close to the star. And in 1999, scientists found the first multiple planet system. It's orbiting Upsilon Andromedae, a star similar to our own sun. Since 1999, several more planets have been found around other stars. Harvard's Robert Noyes headed one of the teams that made the first discovery.
We've surveyed, we and our colleagues, several hundred stars now to look for these planets, and about 3% seem to have these giant planets orbiting close into the stars. Very different from our own solar system, but they are genuine planets in orbit. The real implication of this is that planetary systems are common, and very likely ones that are pretty much like our own may well be common. The reason we haven't seen the ones that are just like our own yet is that they're pretty hard to see.
When we are able to see such planets, we will have taken a step closer to learning the answer to the third term in Drake's equation. NE represents the number of planets that have Earth-like characteristics. Because it's assumed that life, as we know it, will need an Earth-like environment to thrive. Over the next several decades, the United States and other nations will be launching a new generation of space telescopes, many far more powerful than the Hubble Space Telescope. One of them, dubbed the Terrestrial Planet Finder, will specifically seek planets like our own.
And the long-term goal, say in 40 years or so, is to actually be able to image an Earth-sized planet around another star out to a distance of about 40 light years. Now, it won't be a really good quality image. You'll be able to see things like continents and clouds and oceans. Certainly nothing like a spy satellite photo. But eventually, this type of capability, using very advanced telescopes, will tell us, in effect, where are the Earth-like planets? Where are the planets that look like they could harbor life or that may currently harbor life?
That's the fourth term, FL, fraction of Earth-like worlds with life. Recent findings indicate that, here on planet Earth at least, life began at the very first possible opportunity.
Life got started here in a cosmic eye blink. We have a cooling planetary surface and liquid water by about 4 billion years ago.